Most people walk right over the key indicators of diamond-rich ground without ever knowing it. A nondescript rock in a gravel bar, perhaps tinged red or dark gray, might carry the trace minerals that whisper of a diamond-bearing source hidden nearby. Diamond-bearing rocks rarely announce themselves with sparkle or glamour. Instead, they hide in the mundane, pebbles embedded in streambeds, dark nodules near volcanic ridges, or decomposed soils tinged by deep earth minerals. Unlike precious metals, which sometimes appear visibly in placer form, diamonds arrive via violent volcanic events, riding upward from the mantle in explosive eruptions that form vertical intrusions known as kimberlite or lamproite pipes. Over millions of years, weathering erodes these pipes, dispersing their payload across alluvial fans, riverbeds, and sediment layers. This dispersal hides the true origin, but also gives skilled observers the trail to follow. One of the earliest field signs is not the diamond itself, but its mineral companions. Chrome-rich pyrope garnets, metallic grains of ilmenite or magnetite, and even certain chromites often travel farther than diamonds in a stream system due to their relative hardness and resistance to breakdown. These indicator minerals are your first signal. A weathered garnet just a few millimeters across, when found repeatedly in stream traps or benches, can be more important than any speculative digging. To the trained eye, even soil color or texture can serve as early clues. A bluish tint to decomposed kimberlite is often the first layer seen before hitting unweathered volcanic rock. This blue ground signals proximity to pipe material. But it's the context, not just one grain, but a repeatable suite, that confirms you're on a real lead. One garnet may be incidental. A dozen, across multiple trap points in a drainage system, tells you a source lies upstream. Yet, many dismiss these signals. A common pyrope may be misidentified as a reddish piece of glass. A weathered ilmenite grain may go unnoticed in the black sands. The fortune lies not in finding one stone, but in knowing what that stone implies. When you realize a single garnet could trace back to a multi-million-dollar deposit, you stop walking so quickly past dull gravel bars. But what exactly sets these stones apart from lookalikes? The next clue lies in their luster, density, and habit, properties that can be tested by hand, in the field, with little more than sharp observation and a few simple tools. A weathered chunk of kimberlite looks unimpressive to most, just a crumbly, greenish-gray rock dotted with tiny inclusions. But to a trained eye, it's a geologic exclamation mark, a relic of mantle violence, pushed upward in a superheated eruption and solidified into a pipe that may hold the world's hardest mineral. The challenge is learning to recognize it before digging. The first key trait of kimberlite is its texture. Unlike common basalt or granite, kimberlite has a brecciated, porphyritic appearance, meaning it often contains broken fragments, xenoliths, and large crystals, xenocrysts, embedded in a fine-grained matrix. The matrix may feel soft under fingernail pressure, especially in decomposed sections, while the embedded minerals, like olivine, garnet, or even chromite, stand out as harder specks. Lamproite, its less common cousin, may have a more vesicular look with higher potassium content, but both are rooted in deep mantle sources. Another giveaway is weight in hand. Kimberlite, when fresh, often feels heavier than expected for its size, thanks to its mineral content. It has a specific gravity around 2.6 to 3.3, depending on weathering. While this doesn't scream diamond, it helps separate it from lighter surface rocks during field comparisons. Holding and comparing local float samples quickly tunes your intuition toward what's anomalous. Color is also a clue, but a deceptive one. Kimberlite weathers to yellow, brown, or blue-gray tones, depending on local conditions. Blue ground refers to relatively unweathered kimberlite just below surface oxidized layers, and has been historically associated with productive zones, especially in South Africa. Lamproite can show yellows and ochres, often due to iron staining, and occasionally reveals its mantle source through ultramafic textures under magnification. Field context matters just as much. These rocks are never found in isolation. They intrude older crust and typically form pipes or dikes in clusters, often aligned along fault zones. If you find one piece of possible kimberlite float, it's essential to map terrain features. Is it near a drainage that could carry indicator minerals? Are there elevated ridges where erosion might have exposed more? Does the topography suggest a weathered cone or crater structure? Tests can begin on site. A hand magnet may not stick to the matrix, but it might pull on included ilmenite or magnetite grains. Scratching the surface with a knife tip or steel file gives a quick read on hardness, which varies due to the mixed composition but generally feels softer than quartz. UV reaction isn't typically helpful with the host rock itself, though some included minerals, especially diamond under LW, can fluoresce faintly bluish, not diagnostic, but promising. Still, many volcanic rocks mimic the outward look of kimberlite. Basaltic breccias, serpentinite, and even altered andesite can fool the eye. That's where micro-detail becomes essential, spotting the right crystal shapes, the right mineral inclusions, and the right field associations. In many cases, the host rock gives up its secrets through what it leaves behind, not the diamond itself, but the trail of heavy, heat-formed clues now washing downstream. To follow that trail, you'll need to spot the first field-level companions, indicator minerals that appear before any diamond, yet consistently track with its origin. One of the strongest of these is a deep crimson stone often mistaken for a cheap garnet, until its chemistry and context reveal its true significance. Kimberlite pipes don't look like treasure maps on the surface. Most have been scoured down over millions of years, buried under sediment or vegetation, and scattered by glacial movement or erosion. But their shape below ground is surprisingly consistent. Carrot or funnel-shaped intrusions that cut vertically through the crust, often less than 1 hectare at surface but widening below. Finding them means reading terrain like a detective, tracking float material, mineral dispersal, and drainage logic to their eroded roots. In known diamond provinces, historical mapping has identified hundreds of kimberlite pipes, yet only a fraction proved economic. Many carry indicator minerals without hosting gem-grade diamonds. Others have been masked entirely by overburden. But in new or unproven zones, float mapping becomes essential. Explorers grid the region with transects, collecting sediments at stream confluences, benches, or glacial traps. They look not for diamonds, but for durable indicators, pyrope garnet, chromite, ilmenite, which fan outward from the source in recognizable dispersal patterns. The key is narrowing down where that fan begins. In Canada's Slave Craton, for instance, exploration teams used airborne geophysics to identify magnetic lows often associated with kimberlite, then cross-referenced those anomalies with garnet-rich samples. When indicator grains show up consistently in one direction and diminish in the opposite, you're likely downstream from the source. Once you have vector overlap from 3 or more sample lines, you're triangulating a candidate zone, often just a few hundred meters wide. Lamproite behaves differently. Found in places like Western Australia, India, and parts of the US, lamproite fields can host rich diamonds, but their surface expression is messier. Rather than clean vertical pipes, lamproite may erupt explosively and spread across surfaces irregularly, forming bowl-shaped depressions or sills. This makes drainage patterns less predictable, requiring closer terrain reading and sometimes trenching to expose structure. Argyle, one of the world's most productive diamond mines, came from a lamproite source once mistaken for a volcanic maar. Another complicating factor is glaciation. In Canada, glacial till has carried indicator minerals up to 50 kilometers from their source, laying false trails unless the movement direction is accounted for. The same issue occurs in Siberia and northern Europe. Thus, knowledge of local glacial history becomes critical, including ice flow direction, advance/retreat sequences, and terminal moraines. A garnet found in till might have no relation to nearby geology unless its movement can be traced backward along glacial vectors. Even in non-glaciated zones, erosion can confuse the picture. Streams carry garnets and ilmenite grains far downstream, sometimes bypassing deeply buried or fully eroded pipes. That's why indicator mineral counts aren't just presence/absence, they require concentration analysis. 10 garnets per kilogram of sediment may be background noise. A spike to 200 plus garnets/kg, especially with accompanying ilmenite and chromite, signals proximity. Once a concentration zone is identified, the next step is structural. Teams look for vertical intrusions via magnetic surveys, gravity anomalies, or drilling. But before the heavy equipment arrives, a skilled prospector can do much with just sieves, a magnet, and a gold pan, tracing the fan pattern backward through gravel bars and benches. And when that fan tightens into a narrow corridor with high-count garnet hits, it's time to isolate and examine the most reliable of those indicators, a dense, purplish-red garnet that may point directly to diamond-bearing kimberlite, the chrome pyrope. But it doesn't always stand out at first glance, and that's where color, chemistry, and terrain intersect. In a pan of dark concentrates, Many prospectors scan past a reddish grain without pause. It looks like a cheap garnet, something found in decorative gravel or common metamorphic rocks. But if that red carries a faint violet or purplish hue, it could be chrome pyrope, a tracer mineral born in the upper mantle and one of the strongest field indicators of diamond-bearing kimberlite. Pyrope garnet forms under high-pressure, high-temperature conditions deep within the earth, typically over 150 kilometers down. When kimberlite eruptions transport diamonds upward, they often bring along pyrope as part of the cargo. But not just any pyrope signals diamonds. The key variety is CR pyrope, meaning it contains chromium, which lends it a pinkish to deep violet color. This chrome content isn't always visible to the eye, but it often gives a richer tone than almandine or grossular garnets, which dominate surface rocks. In the field, your first test is visual, color and translucency. CR pyrope often appears semi-translucent with a wine red or plum hue. Under strong sunlight, rotate the grain and watch for internal flashes. Shape can help too. Many pyropes weather into rounded dodecahedrons, though fragments are more common. In the pan, they'll settle with other heavies due to their density, 3.7–3.9 Sg, which is noticeably higher than quartz or feldspar. Even before assays, you can begin separating likely candidates by pan behavior and visual signature. If you suspect pyrope, the next step is a simple magnet test. CR pyrope is non-magnetic, unlike many imposters that show faint attraction. Use a rare earth magnet and sweep slowly over your concentrate. Remove any grains that jump. Then perform a water rinse and handpick the remaining reds for closer inspection. A hand lens or loupe helps distinguish surface pitting or internal structure, but the best signal remains the vivid color saturation, especially when wet. The ultimate confirmation, though, is chemistry. Field portable XRF analyzers can detect chromium and magnesium ratios in pyrope grains. The higher the CR and Mg, the more likely they originated in a diamondiferous environment. In professional surveys, grains are often plotted on G9/G10 classification diagrams based on their composition. G10 garnets are closely associated with high-quality diamond sources. But not all garnets with chromium lead to diamonds. Some crustal metamorphic rocks contain CR-bearing garnets from unrelated processes. That's why repeatability matters. Finding one CR pyrope is interesting. Finding dozens in the same drainage, especially accompanied by ilmenite or chromite, builds a compelling case. The clock is always ticking in fieldwork. Weather, land access, or competing claims can pressure decision-making. So once CR pyrope appears in multiple traps along a stream system, it's time to intensify efforts. Map those trap points, record GPS locations, and begin bracketing the dispersal fan. That fan, if shrinking upstream, could be zeroing in on a pipe. Yet, pyrope alone isn't enough. Diamonds have traveled alongside other heavy friends, and the next one carries a unique trait that makes it jump to a magnet, stand out in a pan, and provide a metallic gleam no garnet can mimic. To build confidence in your target, you'll want it to show up too. It takes less than 5 seconds to miss a crucial signal. As you dry your pan concentrates in the sun, a tiny metallic grain clings to the edge, nudged by your magnet, and most people flick it away, assuming it's just black sand. But in diamond exploration, that grain might be ilmenite, a heavy oxide mineral that not only tracks with kimberlite but can reveal the thermal and chemical conditions where diamonds formed or were destroyed. Ilmenite, Fe-TO3, is a common accessory mineral in kimberlite pipes, and like pyrope garnet, it survives erosion and travels downstream. What makes it so useful is twofold: its magnetic properties and its chemistry. Ilmenite is weakly magnetic, especially when oxidized, and responds to a neodymium magnet with a slight creep across a flat surface, often just enough to separate it from inert silicates in the same pan load. In the field, after panning to heavy black concentrates, you can run a small rare earth magnet along the underside of a plastic sheet or pan. Grains that follow slowly and cluster are often ilmenite, magnetite, or chromite, all potential kimberlite companions. Magnetite, the strongest responder, usually signals more mafic or crustal rocks, but its presence isn't disqualifying. Ilmenite's movement is more hesitant, but its luster is the giveaway, a submetallic to metallic sheen, often with bluish or bronze tints when fresh. Shape and surface texture add clues. Ilmenite grains tend to be angular, tabular, or platy. Under a hand lens, some show characteristic pitting or oxidation rims. In weathered form, they may take on a brownish hue, but their density, 4.7, 5.0 Sg, means they still concentrate with garnet and chromite in sieves or pans. Chromite, another key indicator, is non-magnetic but similarly heavy, often dull black with a greasy luster. The most valuable insight from ilmenite, however, isn't just presence, it's chemistry. Laboratory analysis can reveal whether the ilmenite is diamond compatible. High MgO and low Cr2O3 contents are often associated with diamond-stable conditions. Conversely, ilmenites that crystallized under oxidizing conditions might indicate a barren kimberlite, where any diamonds would have resorbed back into graphite. That's why professional labs test ilmenite suites to assess the diamond preservation potential of a pipe, even before bulk sampling. In regional sampling grids, repeated ilmenite hits, especially in conjunction with Cr pyrope, mark a serious lead. If your samples show both indicators increasing upstream, the data becomes directional. You're bracketing the dispersal train toward a source. To maximize resolution, you now shift from wide net sampling to tighter sieve work, isolating specific grain sizes and running repeated traps to verify concentration increases. Tools matter here. A number 40 mesh sieve, 0.425 mm, helps isolate the indicator size fraction. Paired with a magnet sweep and careful drying, you can separate dozens of potential indicator grains from a single kilogram of sediment. Record their counts, log coordinates, and begin plotting trends. If ilmenite and garnet count spike in one area, especially if magnetite remains constant or drops, you're zeroing in on a kimberlite or lamproite pipe rather than general mafic terrain. Still, indicators are only as useful as the process that recovers them. The next phase isn't flashy, but it's where many find or miss their shot entirely. Sifting, panning, recording, and building a repeatable, field-level workflow that scales. It's how the pros turn clues into coordinates. A single overlooked grain can mean the difference between walking away from a fortune and triangulating a viable pipe. The difference isn't luck, it's process. And nowhere is process more critical than in your pan and sieve setup. It's where raw sediment becomes a diagnostic sample, and where diamond indicator minerals reveal themselves through repeatable isolation. Field collection begins at logical trap points, inside stream bends, below waterfalls, behind large boulders, or on terrace benches where heavy minerals settle during flood events. In non-stream areas, sample sites may include colluvial fans or glacial till, chosen based on prior hits of pyrope or ilmenite. From each site, collect around 10 to 20 kilograms of sediment, enough to yield meaningful concentrates but still manageable by hand. Begin by classifying the sediment. Use a nested sieve stack, typically number 20, 0.85 millimeters, over number 40, 0.425 millimeters, to separate coarse from fine. Most indicator minerals fall into the 0.5 to 1.5 millimeters range, and the hashtag 20, hashtag 40 window captures the highest yield size fraction. Material too fine becomes difficult to handle and more prone to false positives from silt-based reflections. Too coarse, and you may miss crucial garnet fragments or small ilmenite grains. Once classified, process each size fraction using a gold pan or battue. The latter, with its broad surface and deep center, offers superior control over heavy mineral separation. Use a circular swirling motion in standing water to suspend and wash away light silicates. Between each stage, inspect the black sands at the base. Heavies, magnetite, ilmenite, chromite, will settle tightly. Garnets and other indicators may appear lodged in the interface zone, just above the black layer. Field documentation is non-negotiable. Record GPS coordinates for every sample site, depth of collection, estimated sediment type, and any anomalies observed, reddish clay layers, bluish decomposed rock, unusually coarse grains. These notes become critical when trends begin to emerge, especially when multiple samples from different points yield consistent indicator patterns. After drying concentrates, magnet separation becomes the next refinement step. Use a neodymium magnet inside a plastic bag to sweep dried material on a flat tray. Magnetite will leap to the magnet. Ilmenite will creep or roll slowly. Chromite remains still. These physical behaviors allow for rapid rough sorting before visual inspection or lab prep. For every 10 kilogram sample, expect just 1 to 5 grams of concentrate, but within that gram may lie the diagnostic suite. Hand-pick grains of interest using tweezers and a hand lens. Isolate pyrope candidates, red to violet, translucent, ilmenite, metallic, bluish-black, weakly magnetic, and chromite, black, high luster, inert. Bag and label each set meticulously. Even at this stage, patterns will emerge. Multiple samples showing CR pyrope and ilmenite hits from upstream zones signal a probable dispersal fan. To visualize this, many field teams use heat maps or concentration plots. For independent searchers, even a hand-drawn topographic map with sample dots and grain counts can be enough. The goal is always directional confirmation, grains pointing back to a common origin. Once a fan converges, trenching or scout drilling becomes justifiable. But premature drilling before the indicator fan is tightened can waste tens of thousands of dollars. Nothing derails an amateur diamond hunt faster than quartz. Clear, angular, and sometimes flawlessly transparent, it's the most common imposter in streambeds and concentrates. Its sparkle fools the eye, especially under strong sunlight or LED inspection. But quartz is just the first layer of deception. More dangerous are zircon, corundum, and synthetic glass, each capable of masquerading as diamond to the untrained observer, and each requiring more than just a loupe to unmask. In the field, quartz often appears in the same sieved fractions as genuine diamond indicators. It has a vitreous luster, high transparency, and can feel heavy when waterlogged. But the moment it dries, its true weight, around 2.65 Sg, reveals it as far less dense than diamond. If you're unsure, perform the heft test. Diamonds are around 3.52 Sg. Even small ones feel dense when dry. With practice, the difference in weight in hand becomes intuitive. Zircon presents a tougher challenge. It shares the high refractive index and adamantine luster of diamond and has an Sg closer to 4.6 to 4.7, even heavier than diamond. Under magnification, zircon often shows fine growth lines or zoning, which diamond lacks. Many zircons fluoresce under UV light in a range of colors, yellow, orange, blue, but so do some diamonds. Color zoning and double refraction offer a clearer distinction. Zircon shows strong birefringence under a polarizing filter or when rotated under a loupe, where facet edges may appear doubled, a key fail for diamond imposters. Corundum, sapphire or ruby in less marketable form, occasionally turns up in indicator suites, especially near ultramafic terrains. It's extremely hard, Mohs 9, and can survive aggressive panning. But it has a duller luster than diamond and a greasy, waxy surface when uncut. It's also more likely to be opaque or colored. Despite its value in other contexts, corundum's presence does not necessarily correlate with diamond-bearing pipes. Synthetic glass and cubic zirconia are the most problematic in second-hand markets, especially when purchasing rough. In the field, glass fragments often show curvature or bubbles when examined under magnification. They lack the hardness, density, and crisp breakage patterns of true diamond or zircon. Cubic zirconia, specifically made to imitate diamond, passes many visual tests but fails others, especially thermal and optical. That brings us to a critical triage step: thermal conductivity. Diamond dissipates heat extremely fast, a property unique among transparent minerals. Handheld testers, available commercially, can quickly rule out quartz, zircon, and glass. Place the stone on a flat surface, test its heat response. A diamond will cause the probe's reading to spike almost instantly. Most imposters won't. Still, thermal tests alone don't eliminate moissanite, which also conducts heat well and fools even advanced testers. It takes optical behavior, specifically the presence or absence of double refraction, to break that tie. But in the early field stages, your best defense against false positives is process. Only test stones that co-occur with indicator minerals, emerge from mapped fans, and pass density and magnet tests. Isolated, sparkly grains in poor terrain rarely justify lab spend. Field efficiency means eliminating 95% of candidates quickly, before lab fees pile up. That's why establishing a testing protocol, visual, density, magnetism, thermal, saves both time and credibility. Yet even after all that, some grains leave enough ambiguity to justify escalation. The next test steps into the physics of materials, using thermal behavior to separate real diamond from the lookalikes that pass the first visual and density screens. And in that moment, one sharp reading can settle the question. A stone can look perfect, weigh right, resist scratching, and still be a fake. That's why seasoned prospectors never trust eyes alone. They reach for thermal conductivity testers. In the field or at the edge of a workbench, one touch from a thermal probe can expose an imposter instantly. Diamond's unique ability to move heat is more than a curiosity, it's a definitive signature. Diamond conducts heat better than almost any known material, 5 times better than copper. This property stems from its tightly bonded carbon lattice, allowing vibrations, phonons, to travel with almost no resistance. Thermal testers exploit this. A heated probe tip touches the stone, and sensors measure how quickly the heat dissipates. If the tip cools rapidly, the device beeps or displays a diamond signal. If it doesn't, the reading flatlines. To run the test properly, the stone must be clean and dry. Oils or water can dampen thermal transfer, leading to false negatives. The stone should also be firmly held, ideally flat side up on a stable, non-conductive surface. Handheld testers vary in sensitivity, but for most field use models, even a small 2 to 3 mm diamond will trigger a positive result if touched squarely. Quartz, glass, and zircon all fail thermal tests. Their structures don't allow for rapid heat flow, and their readings fall well below threshold. Cubic zirconia, one of the most common fakes, gives near zero response. Even corundum and topaz, which score high on hardness, show weak thermal conductivity. This makes thermal testing one of the most efficient eliminators in the prospector's kit. Moissanite, however, complicates the picture. It's the only common simulant that also conducts heat well, sometimes enough to fool entry-level testers. That's why dual-mode testers, thermal plus electrical conductivity, are preferred. Moissanite conducts electricity. Diamond does not. With a tester that checks both, moissanite lights up on both channels, while diamond triggers only the thermal. This two-stage screening is vital when your candidate passes visual and density checks. Still, field conditions aren't perfect. Cold weather can skew readings. Small stones may require precision placement. And battery-dependent devices can fail after a long day. That's why testers shouldn't stand alone. They should confirm what field indicators already suggested. High-density, non-magnetic stones found in indicator-rich sediments from an upstream source. If a stone passes thermal and fails electrical conductivity, your confidence rises, but it's not yet proof. Thermal testing is a binary filter. It excludes, but doesn't guarantee. For confirmation, you'll need a test that quantifies, one that reads not just heat or electricity, but buoyancy. That's where the next test comes in, a classic method that dates back over a century and still separates real from fake with quiet precision. It requires nothing more than water, string, and a scale. A rough, uncut diamond feels deceptively small in the palm, but it's heavy for its size, far denser than quartz, glass, or even garnet. That subtle weight in hand can guide intuition, but it's not proof. To truly separate diamonds from imposters, you need to measure specific gravity, SG. And the simplest way to do that, even in a field camp, is through water displacement. Specific gravity is the ratio of a material's density to that of water. Diamond clocks in at approximately 3.52, meaning it's 3.52 times heavier than an equal volume of water. Most common fakes fall short: quartz, 2.65, glass, 2.4, 2.6, and cubic zirconia, 5.6, 6.0. By calculating SG, you can often eliminate these candidates in one session. The setup is basic: a precision scale, accurate to at least 0.01 grams, a cup of water, and a length of thin thread or a wire cradle. First, weigh the dry stone in air. Record that mass, let's say 1.41 grams. Then suspend the stone in water without touching the sides or bottom. Weigh it again while submerged. Say it now reads 1.01 grams. The difference, 0.40 grams, represents the volume of water displaced, which equals the stone's volume in cubic centimeters. Now divide the dry weight by the displacement. 1.41 divided by 0.40 is equal to 3.525. That's right, in diamond territory. If it were quartz, the result would hover around 2.6. Cubic zirconia, which often fools thermal tests, would produce an SG over 5.5, clearly out of range. Zircon sits around 4.6 to 4.7. This makes SG testing a powerful cross-check against thermal readings, especially in borderline or suspicious cases. For best results, use distilled water at room temperature and ensure no air bubbles cling to the stone. Perform the test at least twice to confirm consistency. Stones with irregular shapes can trap bubbles or shift in water, so gently agitate the setup to stabilize readings. If you're testing multiple stones, keep them labeled and logged with all other data: location, sieve size, indicator presence. Field adaptations exist. Some use syringes or graduated cylinders to measure water displacement volume directly, especially when a scale isn't available. Though less precise, this still gives a rough SG estimate good enough to exclude obvious fakes. For prospecting kits, compact SG scales are available that include cradles and tare functions, making it possible to run this test in remote zones with little setup. The key is cross-verification. If a stone shows high SG, passes thermal testing, fails electrical conductivity, and comes from an indicator-rich sample, it becomes a strong candidate. But even then, final confirmation should wait for more context. A single stone can mislead if it traveled far from its origin. Worse, old erosion trails can lead searchers to depleted or misinterpreted sites. A flash of CR pyrope in a streambed. A heavy, lustrous ilmenite grain nearby. Even a dense, thermally conductive pebble that passes SG testing. It feels like the trail is tightening. But surface finds can be treacherously deceptive. The farther you are from the source pipe, the more erosion, glacial transport, and hydrodynamic sorting distort the story. In fact, some of the richest-looking traps turn out to be tailings of erosion, decades, even millennia, downstream from the real source. Kimberlite and lamproite pipes rarely expose themselves cleanly. Most are buried under glacial till, vegetation, or thin soil layers. Over millions of years, weather and ice erode the upper cones of these intrusions, dispersing indicator minerals across wide fans. This creates a challenge. You may find a dense suite of pyrope, chromite, and ilmenite in a single drainage, and still be 10 to 15 kilometers from the eroded pipe. Worse, if glacial movement intervened, the entire fan could have shifted sideways or even reversed in slope. In areas with high erosion rates, like tropical laterite zones or mountainous river systems, the original kimberlite material may be gone entirely at surface. What remains is an alluvial or colluvial concentration of durable indicators. Diamonds, due to their extreme hardness and hydrophobic surfaces, may travel far with minimal wear. But so do their companions. Without understanding terrain history, a rich sample can lead to fruitless trenching. That's why terrain context matters as much as mineral presence. If indicators occur only in lowland drainages, but not in higher tributaries, you may be too far downstream. The ideal pattern shows increasing indicator counts as you move upstream, eventually tapering off, a classic dispersal fan closing in. When counts suddenly drop or vanish uphill, that's your clue. The source lies between those last two hits. Elevation modeling helps. Digital elevation maps, DEMs, LiDAR, or even detailed topographic maps can reveal benches, paleochannels, and relict river courses, critical when modern rivers have shifted. In some cases, the original drainage that carried diamonds has long since dried up or been buried by landslides or glacial overburden. Field teams look for terrace deposits, old meander scars, and coarse gravels resting atop bedrock, signs of ancient transport that predate the current flow paths. False leads also arise from anthropogenic movement. In mining regions, indicator minerals or even diamond fragments may appear in fill, spoil, or reworked sediments. A seemingly natural setting can host reprocessed material from upstream operations. Historic gold camps, road fills, or hydraulic tailings all distort context. This is why chain of custody and clear provenance is essential even for rough stones found in the wild. Field grids offer protection against these traps. By sampling in a repeating, structured pattern, say, every 500 meters along a drainage, with perpendicular crosslines, you collect data that tells a spatial story. When graphed, true dispersal fans appear as cones or plumes. Erratic or scattered hits suggest transport, contamination, or old erosion zones now distant from the original pipe. That's where many prospectors falter. They dig too soon. Surface hits tempt action, but without directional confirmation, trenching drains resources fast. Before committing to subsurface work, the smarter path is to gather more mineral data, from a zone often underestimated, the indicator mineral suite of lamproite fields, where the usual rules bend and lead to one of history's biggest diamond reversals. For decades, exploration focused almost exclusively on kimberlite. Its vertical pipes, classic indicator suites, and mantle-derived signatures gave geologists a relatively stable model to chase. But in the 1970s and 80s, a quiet revolution occurred, first in Western Australia, then in parts of India and the United States, when diamond-bearing lamproite fields began yielding commercial-grade stones. The catch: lamproite broke the kimberlite rulebook, both in mineralogy and behavior, and those who clung to the old model missed enormous potential. Unlike kimberlite, lamproite isn't tied to deep cratonic roots. It can erupt in younger terrains, even mobile belts where traditional diamond stability zones aren't expected. It often forms broad, irregular intrusions, not clean, vertical pipes, and weathers to soft, clay-rich soils that conceal structure. The Argyle pipe in Western Australia is the most famous example, a diamond source in Proterozoic terrain, low in classic indicator minerals, but rich in small, deeply colored stones, including the rarest of pink diamonds. Lamproite's mineral suite overlaps with, but deviates from, kimberlite indicators. You may still find pyrope garnet, but often in lower abundance. Instead, look for phlogopite mica, large, golden-brown plates that sparkle in sunlight, often mistaken for biotite. Leucite and sonidine, potassium-rich felspathoids common in lamproitic melt. Perovskite and richterite, less common but diagnostic under thin section or probe analysis. But these minerals degrade quickly. Lamproite is chemically reactive and weathers fast, making its signals more subtle in surface samples. Its ilmenite may be altered or entirely absent. Chromite can still occur, but with lower Cr2O3 content, weakening its reliability as a standalone indicator. That means prospectors must learn to read soft signs, paleochannels with yellow clay, friable rocks with mica flakes, or even diatomaceous textured soils under ephemeral grass cover. Texture provides another hint. Lamproite often forms tufaceous breccias, explosive, fragmented rock textures filled with lapilli and volcanic bombs. These can feel gritty or greasy when wet, breaking apart with a fingernail or low-pressure probe. In cross-section, lamproite may appear as flat-lying sills or shallow crater infill, not vertical cones, changing how geologists interpret resistivity or magnetic data. Geophysical tools still work, but results differ. Lamproite may show as a magnetic low due to its weathered nature, or present a complex gravity signature. Resistivity surveys can help in dry zones, especially when chasing clay-rich pockets that contrast with surrounding rock. Still, the best lamproite discoveries began not with instruments, but with patient, detailed surface mapping, combining float sampling, micaceous indicators, and trenching into unconsolidated soils. Argyle's initial discoverers misclassified the pipe as a volcanic maar. Only when indicator garnets appeared upstream, and lab tests showed high-pressure deformation in xenoliths, did the team reconsider. The field's unique geology shattered assumptions. Productive diamonds could come from younger terrains, altered mineral signatures, and even heavily weathered rock. This lesson applies globally. In India, lamproite-hosted stones have emerged from the Bhattar Craton. In Arkansas, the Crater of Diamonds Park sits atop a lamproite field still open to public digging. Each of these zones taught a vital truth. Indicators must be interpreted within geological context. No single mineral guarantees diamonds, but patterns, terrain, and chemistry together tell the real story. And sometimes, even that story turns on its head. Because the most trusted indicator mineral of all, chromite, can betray your confidence, sending explorers deep into false zones unless one test, often delayed, catches the truth in time. After weeks of sampling, you finally see the pattern emerge. Black, heavy grains clustering in stream traps, magnetic creep confirming ilmenite, red flashes of pyrope, and thick concentrations of what appears to be chromite, a promising indicator mineral tightly linked with diamondiferous kimberlite. The grid is closing. All signs point upstream. But when the grains hit the lab for electron microprobe analysis, the report stings. They're not chromite, they're spinel. Chemically close, physically identical to the eye, but geologically misleading. This is where many field efforts collapse. Spinel and chromite both form dense, opaque, black grains. Both resist weathering and show up in pan concentrates. But only chromite, specifically low T, high Cr2O3 varieties, has a proven association with diamond stability fields. Spinel, especially aluminous types, can occur in a wide range of crustal rocks, including basic metamorphic terrains or ophiolite belts that have nothing to do with diamonds. Under a hand lens, they're nearly indistinguishable. Both have a dull to greasy luster and rounded grains in alluvial contexts. Magnetically, they behave similarly, weak to non-magnetic. Their density ranges overlap. Chromite 4.4, 4.8 Sg, spinel 3.5, 4.1, with overlap depending on composition. Visual triage fails. This is where field teams that skip confirmatory tests fall into the trap. A spinel-rich zone, especially downstream from mafic-ultramafic bodies, can mimic the signature of diamond-rich kimberlite, but yield nothing on trenching or drilling. Worse, it can waste critical budget and time. The error often comes from rushing the transition from sampling to excavation based on surface grain counts alone. Electron microprobe or SEM, scanning electron microscopy, with EDS, energy dispersive X-ray spectroscopy, is the standard for resolving the difference. Chromite shows dominant CR and Fe peaks, sometimes with Mg or T depending on source. Diamond-associated chromite tends to have Cr2O3 greater than 60 Wt% and TO2, 1 Wt%. Spinel, meanwhile, leans toward higher Al content, with Cr often below 40 Wt%. In some terrains, ferrian spinel complicates the line further, sitting chemically between chromite and magnetite. If lab access is delayed, a field stopgap is to sample host rocks in situ. True kimberlite-derived chromite often occurs embedded in brecciated volcanic matrix, not just as float. Spinel, conversely, may occur in schist zones, serpentinized dunite, or metamorphic contexts unrelated to any volcanic system. Cross-referencing with terrain maps, geological surveys, or satellite imagery can help rule out spinel-prone zones. This chromite/spinel confusion is especially common in orogenic belts or abducted ophiolite zones, where serpentinized rocks dominate. In these zones, spinel is common, while kimberlite is rare or absent. In fact, some of the most convincing indicator trains in northern Pakistan, parts of Turkey, or Central Asia turned out to be spinel misreads, leading to fruitless drilling. The psychological blow from this kind of reversal is heavy. You've invested weeks, possibly months, built maps and momentum, and now face the reality that the trail you trusted has forked in the wrong direction. But the data isn't wasted, not if you integrate the lesson. When trusted indicators fail, the next logical move is to cross-check all hits with standardized classification schemes, like the G9/G10 system for pyrope or TO2 cutoffs for ilmenite. The point isn't to confirm one mineral, it's to validate the entire suite. And when the suite fails, you pivot. That pivot starts by anchoring your process to established workflows used by major survey teams and geological institutions. Their discipline in grid sampling, verification, and multi-test sequences is what turns data into confidence. And that structure, often skipped by amateurs, is the next critical phase in narrowing a target without another costly misstep. What separates a hopeful amateur from a successful field geologist isn't luck, it's grid discipline. Professionals don't follow one promising stream sample straight to the shovel. They build a network of data points, evenly spaced, precisely recorded, and methodically processed, to triangulate a deposit with mathematical confidence. This isn't about chasing glitter, it's about eliminating guesswork. The standard workflow begins with regional reconnaissance. Teams start wide, collecting stream sediment samples across tens or even hundreds of square kilometers. Sites are spaced at fixed intervals, often 1 to 5 kilometers apart, depending on terrain and logistical access. Each sample includes 10 to 20 kilograms of screened sediment, typically processed through number 20 and number 40 mesh sieves, then panned or concentrated on site. Sample points are logged by GPS with sub-meter accuracy, tagged with field notes on surrounding geology, visible float, stream energy, and sediment color. At this stage, the goal is to identify anomalous clusters of indicator minerals, not to pinpoint a pipe. Each sample is dried, magnet-swept, and hand-picked for potential pyrope, ilmenite, chromite, and other indicators. Once a few anomalous sites are found, teams tighten the grid. New samples are taken at closer intervals, say 250 or 500 meters, along the same drainage and perpendicular transects. This helps define the shape of the dispersal train. If indicator counts increase upstream and diminish in other directions, a fan begins to emerge. Professionals plot this in software like ArcGIS or Leapfrog Geo, building layered models that integrate elevation, hydrology, and bedrock geology. But raw counts aren't enough. Every promising grain is lab-tested, usually with electron microprobe or SEMEDS. Pyropes are classified by the G9/G10 system. G10S, with high CR and low Ca, are associated with diamond stability fields. Ilmenite grains are analyzed for MgO, Cr2O3, and TO2 to assess mantle origin and oxidation state. Chromites are screened for CR/T ratios. The goal is not just to confirm indicators, but to rule out barren sources. In parallel, geophysical surveys may be initiated. Magnetic, gravity, and electromagnetic methods are used to identify vertical anomalies suggestive of kimberlite or lamproite pipes. In kimberlite-rich areas, a magnetic low may indicate deep weathering or clay-altered pipe rock. In lamproite terrains, subtle gravity highs or radiometric anomalies may guide further trenching. Once a dispersal fan converges to a narrow zone, ideally within 200 to 400 meters, and the indicator chemistry supports a diamondiferous source, trenching begins. Shallow pits or trenches are dug perpendicular to flow paths to expose bedrock or unweathered pipe material. Teams look for telltale signs: breccia, xenoliths, indicator-rich soils, or blue-ground, decomposed kimberlite. If visual confirmation is still lacking, auger or reverse circulation drilling may follow. Sample handling during this phase is clinical. Contamination ruins credibility. Tools are cleaned between sites. Bags are sealed, labeled, and logged in chain of custody systems. Every grain is accounted for, every sample traceable. The professionalism here isn't aesthetic, it's foundational. In a discovery with potential millions at stake, reproducibility is the only safeguard against error or fraud. Even in successful grids, surprises arise. Missing pipes, indicator reversals, false anomalies. That's why repeatability is key. If two independent sampling passes yield the same fan, same mineral chemistry, same directional logic, the confidence level spikes. Only then does a team justify larger expenditure: bulk sampling, mini-bulk processing, and eventually valuation of rough stones. This grid approach doesn't only apply to institutional teams. Solo prospectors or small partnerships can adapt the model. Consistent spacing, careful labeling, layered testing. It takes more time, but prevents wasted trenching and misreads like the chromite spinel fiasco. And it also clarifies the bigger picture. What works in one terrain might fail in another. A chrome pyrope in northern Canada may mean you're closing in on a diamondiferous kimberlite. The same mineral found in Brazil might just be a fluke from a metamorphic terrain. Indicator reliability doesn't travel well. It changes with tectonics, erosion history, climate, and even glacial behavior. Understanding these regional differences is critical. Without it, prospectors apply the wrong model in the wrong terrain and walk straight past viable targets or dig into barren rock. In cratonic regions, like the Canadian Shield, Siberian Craton, and parts of South Africa, kimberlite pipes intrude ancient, stable continental crust. Here, indicator suites are textbook: G10 pyrope garnets, ilmenite with favorable TO2/MgO ratios, Cr-rich chromites, and high-purity peridatitic xenoliths. These terrains often host deep, intact pipes that retain their original geophysical and geochemical signatures. But glaciation complicates the signal. In Canada and parts of Russia, glaciers transported indicators tens of kilometers from their source. This means mineral trains can be long, and orientation requires precise knowledge of historical ice flow direction. In non-glaciated, tropical cratons like Brazil's São Francisco or Central Africa's Congo Craton, indicators may remain closer to their source, but are often deeply weathered. Pyropes degrade in acidic soils, ilmenite oxidizes and breaks down, and chromite can become coated or altered. Here, the absence of indicators doesn't always mean absence of source, just a deeper or more eroded pipe. Sampling must include deeper trenching or pit sampling into lateritic profiles. Surface float often misleads due to extensive chemical weathering. In mobile belts, such as India's Eastern Ghats or Western Australia's Halls Creek orogeny, the story gets more complex. Lamproite-hosted diamonds dominate, and the indicator profile shifts. G10 garnets are rare or absent. Instead, micas, sonidine, and weathered felspathoids become key. The Argyle deposit, for instance, yields extremely few classic indicators, yet remains one of the most productive diamond mines in history. In these zones, chemistry and geology override standard models. Soil and float mapping, coupled with microprobe assays, become more important than traditional panning. Arid environments like parts of Australia or Botswana offer high visibility but come with sorting challenges. Wind-blown deflation concentrates indicators in patches, decoupling them from upstream movement. Coarse indicators may remain close to the pipe, while finer grains are lost to dust storms. Here, close spacing grids, soil geochemistry, and ground-penetrating radar sometimes replace traditional sediment sampling. Visual float, often ignored elsewhere, becomes more relevant when terrain exposes volcanic breccias or nodular mantle fragments. In flood-prone river systems, such as Southeast Asia or Equatorial Africa, high-energy seasonal flows remix sediments and scatter indicators across complex benches and terraces. Diamond stability under transport becomes critical. Only the hardest, cleanest stones survive, and their indicator trail may be smeared over wide floodplains. Mapping must account for paleochannels and seasonal deposition, sometimes requiring dry season-only access or satellite-based terrain analysis to identify old stream courses. These regional filters matter because value expectations also shift. In Siberia, diamond pipes may yield large, gem-quality stones. In Argyll, the value comes from color, vivid pinks and reds, rare globally. In India, tiny, fibrous diamonds occur in abundance, but few are gem-grade. This affects not just sampling, but economic models. What grade justifies trenching, what chemistry signals potential, and what trade-offs between size, color, and clarity matter locally. Every indicator mineral carries contextual weight. A pyrope in northern Alberta might trace a viable pipe. The same mineral, found in a meta-ultramafic belt in Colorado, might be relic metamorphic. Without regional correction, the same lab result tells two different stories. By the time a stone has passed thermal conductivity, weight in hand, and specific gravity tests, most prospectors start to believe. It sparkles. It's heavy. It's thermally responsive. But one final imposter still lurks: moissanite, silicon carbide, a lab-grown material that mimics diamond in almost every property but one. Its giveaway: double refraction, a visual trait that exposes it under magnification when everything else aligns. Moissanite's danger lies in its strength as a mimic. It scores 9.25 on the Mohs scale, second only to diamond, and conducts heat well enough to trigger most diamond testers. It has a high specific gravity, 3.2, often close enough to diamond to pass water displacement tests with error margin. Even its luster is adamantine, creating brilliant flashes and crisp facet edges when cut. In rough form, it's harder to distinguish. Moissanite grains can be clear, glassy, and angular. Their fracture surfaces and inclusions sometimes mirror those of genuine diamond. And since moissanite is manufactured and distributed in many countries, it occasionally ends up in gravel fill, tailings, or secondary markets, especially in artisanal mining regions or reused sediment fills. But moissanite has an optical flaw: birefringence. It's doubly refractive, meaning light entering the crystal splits into two rays. The result is facet doubling, a visible doubling of edges when viewed under a 10x loupe or gem microscope. If you slowly rotate the stone, edges that should appear crisp and singular start to shimmer or split. This effect is subtle, but unmistakable once learned. Diamond, by contrast, is singly refractive. Its facet edges remain clean and sharp, no matter the viewing angle. In side-by-side tests, trained gemologists rely on this alone to distinguish the two, especially when other instruments are unavailable. To perform this test, use a strong, cool light source and a jeweler's loupe. Examine facet junctions, especially on pavilion or girdle areas, and look for ghosting, blurring, or doubled lines. Moissanite often shows doubling even in small stones, especially along inclined edges. Stones with significant doubling should be isolated and flagged, no matter how convincing the thermal test appeared. If available, a polariscope further confirms this. Moissanite will show light behavior under rotation, while diamond remains dark at all angles. Another backup is electrical conductivity testing. Moissanite conducts electricity, diamond does not. Dual testers are available that run both diagnostics in tandem, a must-have for serious field operations or buying trips in high-risk markets. This final filter is vital, not only to avoid misidentifying synthetic moissanite, but to protect sample integrity. Lab-grown moissanite may inadvertently enter field samples through contamination, fill materials, or even as deliberate fraud. Without optical checks, even experienced prospectors have been fooled into declaring a site promising based on recovered diamonds, only to later discover a backhoe bucket had scraped old road fill or minor tailings seeded with synthetic stones. The lesson here is blunt. No single test is proof. But the right sequence of tests, visual, magnetic, thermal, SG, and optical, tightens your confidence until only genuine stones remain. And once you've weeded out all the imposters, you face the next step, protecting your chain of custody. Because what's in your sample bag now might just be worth a fortune, but only if it's provable, documented, and untampered. And that's exactly where most hopeful finds go to die. Not in the field, but in the handling that follows. It's not erosion, imposters, or poor sampling that kills the majority of credible diamond leads. It's mishandling. A diamond found without documentation is just a stone with a story. That's why professional teams, academic researchers, and exploration companies enforce one rule above all: preserve the chain of custody from field to lab. Every sample, every grain, must be traceable. If not, its value, credibility, and even legality evaporate. Chain of custody begins in the field. As soon as a pan yields promising material, the sample must be isolated and labeled with precise coordinates, collection depth, sieve size, and test conditions. Field tags must be waterproof, tamper-proof, and redundantly marked, ideally with both pen and printed codes. Sample bags, usually made of Tyvek or polyethylene, should be sealed with serial-numbered security tags or tamper-evident tape. From that moment, a written and signed log follows the sample. Who collected it? At what time? Under what conditions? Who handled it next? If a technician dries, sieves, or reprocesses the sample, their name and timestamp go into the log. Even under informal operations, this process is scalable. A simple field notebook and signed zip tie system can preserve sample legitimacy and make the difference between a marketable discovery and a dismissed claim. Tampering isn't always malicious. It often arises from convenience, mixing batches for drying, storing unlabeled concentrates together, or using contaminated pans between sites. But the effect is the same. You can no longer prove the origin of a key grain. And once doubt enters, buyers, labs, and authorities may discount the entire find. In formal exploration, chain of custody continues through transport and storage. Samples are boxed and numbered, and their transit is logged, whether moved by vehicle, courier, or air freight. In sensitive cases, samples are even accompanied by sworn statements or digital tracking devices to monitor temperature, pressure, or tampering. Labs like GIA, SGS, and SRC will reject samples that show signs of contamination or lack origin documentation. When rough stones are involved, the chain of custody carries legal and financial implications. Countries with strict mineral ownership laws, like Angola, Botswana, or Canada, require documented provenance before stones can be exported, cut, or sold. A field find without documentation may be deemed state property, or worse, classified under conflict mineral regulations. In many regions, even possession of undocumented diamonds is prosecutable. For small-scale operators, there are low-tech solutions. Digital photos of each sample at the collection site, with visible GPS units, date stamps, and sample bags, create a visual audit trail. Hand-signed chain of custody sheets protect against internal disputes or buyer skepticism. Secure storage, even a locked toolbox, reduces tampering risk before lab submission. When samples reach the lab, chain of custody continues in internal logs. Each step, receiving, drying, sieving, heavy liquid separation, probe analysis, is timestamped and assigned to technicians. Final results include a reference to the original field sample code. If your field process was sound, this link remains unbroken, and the lab report becomes defensible even in court or international valuation. Fraud is a real threat. In recent decades, several high-profile diamond discoveries were later exposed as salting scams, either by planting synthetic stones in samples or faking field logs to inflate value. These events have made labs, buyers, and governments intensely cautious. Without an intact chain of custody, even a flawless stone may be worthless. But when the chain is preserved, from stream to sieve to scanner, even a single stone can hold immense weight. It becomes evidence, not just a curiosity. And once verified, it demands the next critical step, deciding when to escalate. Because sending samples to a lab too soon can waste money, and waiting too long can lose the opportunity. So how do you know the right moment to ship, scan, and spend? The answer lies in the logic of repeatability and the test grid that makes your find real.